My name is Terrence Barkin. I'm the Executive Director of the Graphene Council, and we're hosting today's webinar series on graphene and energy storage devices, including batteries and supercapacitors and all those different chemistries that are working on in this sector. And with that, we're going to go to our next presenter, Dr. Bo Zhang. How are you, Dr. Zhang?
Thank you. Today I'd like to talk about graphene-enabled lithium-ion battery and lithium-metal battery, and we'll take a deep dive into how graphene can help solve some of the problem of lithium-ion battery and lithium-metal battery. So back in 2002, I filed the first patent on graphene. And this is the from the page of the patent application. And then after that, we began to work on various different processes of producing graphene and graphene oxide, and also the application. For example, in 2004, we filed several patents, and one is on chemical production process for graphene oxide, and then also graphene for hydrogen storage and fuel cell. And then in 2006, we invented graphene-based supercapacitors. I know yesterday we had a speaker talking about supercapacitor. We actually inventor of this technology. We also invented in 2006 the so-called supercritical. 2007, that was a very busy year. We established this company called Enxon Material to begin to produce some graphene and graphene oxide. And then along the way, we invented the graphene-enhanced anode. And then we are the one who invented the so-called liquid phase exfoliation. And then also electrochemical exfoliation of graphene, and also the graphene-based thermal films. And yes, we do also invent the graphene-based aluminum ion cell. We had a very strong IP position here. And we also work on sulfur cathode, graphene-enabled sulfur cathode, etc. In 2016, we finally incorporate or integrate several companies into this Global Graphene Group. And this is where we stand right now. In 2019, we established a pilot scale production facility for graphene-enhanced silicon anode materials. So we began commercialization of our graphene product, graphene silicon anode product as early as 2019. And talking about our patents, so we do have, as a company, we had about 720 patents. And then out of that, approximately 500 patents are related to various different aspects of batteries, including lithium-ion battery anode, cathode, lithium-metal battery anode, and lithium sulfur cells, and even sodium-ion battery, magnesium-ion battery, aluminum-ion battery, etc. We are, And one of our patent, actually the very first patent that was filed in 2002 was noted as one of the 15 patents that changed the world. Actually, the other invention include like iPhone, GPS, and 3D printer, etc. And just about 3 weeks ago, Global Graphene Group was named the Global Top 100 Innovators by LexisNexis, and we are very proud of this accomplishment. Now, let's go down to the battery business here. So the conventional lithium-ion cell have reached their performance limits. The industry is looking for a revolutionary design for next generation EV battery. Very briefly, in terms of energy density, majority of the automobile or EV right now make use of the lithium-ion battery that has a cell energy density below 300 watt-hour per kilogram, typically between 240 and 260 watt-hour per kilogram or so. The industry is looking to extend the EV driving range by increasing the energy density we can achieve that. And here at Global Graphene Group, we have for over the last 15 years or so, we have stayed focused on the energy applications of our graphene. And then for EV battery application, we have been working on the so-called graphene-enabled silicon-rich lithium-ion cells and also graphene-protected lithium metal batteries. Okay, and our lithium metal battery can be manufactured using the current lithium-ion production equipment without having to build a new supply chain. And if you look at silicon, which is right now the hot topic in the lithium-ion battery industry, because traditionally lithium-ion battery make use of the natural graphite or artificial graphite as the anode material. And the graphite itself has a limitation in the sense that the specific capacity of the graphite is typically between 340 up to about 370 milliamp hour per gram. In contrast, silicon itself can store up to about 4,000 milliamp hour per gram. It's almost like 10 times of the specific capacity of the graphite. Well, this does not come without a problem. So when you charge your battery, lithium ion get diffused into your silicon particle, for example, and then these upon repeated expansion and shrinkage of the silicon particle, the particle become pulverized, become many pieces, and that will that creates some very severe problem. In other words, that those pieces of graphite will lose contact with your conducting network. Also, upon repeated deformation, volume expansion and shrinkage, etc., the entire anode electrode can get disintegrated. Okay, that will also create a very severe problem as well. And then if you make use of the liquid electrolyte, then there will be some repeated formation and destruction of the so-called solid electrolyte interface, or SEI, that will consume your electrolyte and consume the lithium ions as well. So, so back in 2007, we began to work on graphene application in the battery area. For example, in 2007, we filed the world's first patent on graphene application in battery. And at that time, we used graphene as a conducting additive, as a supporting substrate, or as a composite ingredient. Okay. And then later on in 2008, we incorporate silicon and then graphene and then a carbon matrix into a composite particle like this. Okay. And then later in 2009, 2010, we use graphene as an encapsulating layer. In other words, that graphene is not a conducting filler anymore. Okay. So as you can see that graphene really can do a much better job if you don't just use it as a conductive additive in an electrode. Graphene can actually help build a robust three-dimensional network of electron conducting pathway. For example, if you have the graphene encapsulated in all those silicon particles, okay, then you can see that this green color saying they can form some conducting network, as you can see here also. So we need to think, as the graphene scientists, we need to think beyond just using graphene as a conducting additive. I think the entire industry appears to go in that direction right now. And so this is an SEM picture of our product here, that as you can see that we have those very thin, visible graphene sheet on the outside here that encapsulating the silicon particles and along with other ingredients inside these secondary particles. And we use the Hawker's iron beam to cut the cross section, and then we can see the internal structures here. So our silicon graphene composite structure has the following features. Our graphene shell can help prevent the entries of organic solvent that otherwise will lead to a repeated formation and destruction of the SEI layer, and that will continue to consume lithium ions. We also have some built-in hole or porosity here to reduce or eliminate the secondary particle expansion. In other words, you don't want your particle to get expanded. Okay, sorry. And so we also have our graphene not only stay on the outside, but also stay inside of the secondary particle. And that forms a very robust 3D network electron conducting pathway. And the graphene's high electrical conductivity can improve the silicon utilization. We also have our own technology of producing silicon nanoparticles. And of course, we started to supply graphene back in 2012. So we have a self-sustaining graphene supply here. Now, this is our product here. And we had a anode material that has a specific capacity up to about 3,000 milliamp per gram, as opposed to 350, 360 milliamp per gram for graphite. Okay, and we have we certainly has a very good product here that we actually received an award, so-called R&D 100 award in 2018 here. This is some of the cycling data that we have been able to obtain here. And then these are full cell data, not just the so-called half cell data. And for example, in this particular case here, we can cycle our silicon anode material up to about 800 cycles. And for silicon anode material, this is really exceptional. The next topic that I will talk about is the so-called lithium metal battery. In the case of lithium-ion battery, you use either graphite or now you can use silicon as the anode material. But for the so-called lithium metal battery, you make use of the lithium metal as the anode active material. Okay, and that, of course, the lithium metal itself has a very high specific capacity, but it also comes with some type of problem. Okay. One problem is that there is continued reaction or electrochemical reaction between the liquid electrolyte and the lithium metal itself. And also there is a so-called lithium dendrite issue or so-called dead lithium particle issue. And then there are, in so-called solid state electrolyte, there are large gap or very poor contact between the so-called lithium metal layer and the solid electrolyte separator. And that leads to very high internal resistance. And this is a little bit some of the chemistry here. I'm not going to go into the detail here. So the point here is that if you allow your liquid electrolyte to continue to contact the lithium metal, then there is a problem. You continue to corrode your lithium metal, continue to create some very severe issues. So there's another issue that is the so-called lithium dendrite here, that in theory, when you departed your lithium metal from the cathode back to the anode, presumably you should form homogeneous departition of your lithium metal, but things don't go that way. So it go in a very inhomogeneous manner, and eventually some of the so-called dendrite actually protruded out just like this, and you will penetrate through your separator, go into the cathode that will create a so-called internal shorting. And then presumably that can lead to explosion as well. The number three is that if you have, for example, your lithium metal here on your anode, and then during discharge, the lithium metal get dissolved and then goes to your cathode side. So you will create a gap here. And so typically in industry, you will use a very high holding pressure to your battery stack. And that is really undesirable. So how can we help? I mean, how does graphene help to improve the performance of lithium metal battery? Well, we have several approaches. Okay, one is that we can use some type of graphene sheet, high surface area graphene sheet, and implement it here on the surface of the lithium metal, and that can prevent dendrite from getting initiated. And then let me very quickly explain this. And we published a paper in Energy and Environmental Science, so I'm not going to go into the detail. So in short, by implementing our graphene sheet in an anode, we significantly increase the specific surface area of our anode. And because of that, the so-called exchange current density, J, will be significantly reduced. Okay? And the so-called dendrite initiation time will be inversely proportional to J to the square. So it will take, if you reduce the exchange currency, current density, you essentially increase the time that is required to initiate the dendrite to almost infinite. Okay, and then similarly, if you happen to form some type of dendrite, then the dendrite tip will need to will grow. Let me see. Okay. And then if you look at the dendrite tip here, the growth rate is actually proportional to your so-called exchange current density also. So if you reduce the exchange current density, you can significantly reduce the growth rate or essentially stop the growth of the lithium dendrite. And then there's some of the experimental data to show that indeed by implementing the graphene sheet in an anode, that we had a very stable and uniform deposition of our lithium metal back to the anode site. The second approach that we use is to use the so-called graphene foam. In other words, that we introduce some what we call lithophilic or lithium attracting metal into the graphene foam in the internal site. This is the metals such as silver and others. You can introduce that. Then the graphene foam itself is a highly elastic structure, so it will expand and shrink when your lithium metal actually gets shrink or get expanded. And so that will help you maintain a good contact between the lithium metal and the solid state electrolyte. So we have a so-called enabling technology of a solid state battery industry right now. And we also have introduced certain lithophilic lithium metal into our foam. And the pores are actually very stable host for the lithium deposition. Another approach that we have taken by using graphene is to form the so-called graphene ball. Schematically, that we have graphene inside here and also outside, and then of course inside you have a lot of high level of porosity. Again, you also introduce those lithophilic metals. And again, this one can take care of, can address the so-called dendrite initiation and propagation issue here, right? And also because of the presence of those transition metal elements that it serves as a preferred site for lithium metal deposition. And we allow the lithium metal to get deposited onto the surface of graphene here inside the structure in such a way that there will be no dendrite. And then the internal pore, again, will provide the stable host for the lithium metal here. Sorry, some reason. All right. And because of that, we have been kind of continuing to improve our graphene-enabled lithium metal battery. You know, we'd like to reduce the amount of lithium metal. If you are able to reduce it down to essentially zero, then you have the so-called anodless lithium metal battery that will reduce the cost and also the volume and the weight of the entire battery, and thereby increasing the energy density of the battery. And again, these are some of the data that I can show you here. I can share with you full cell data that shows that by implementing the graphene, we are able to have achieve very stable cycling behavior. In contrast, without graphene, the battery quickly fail. And then we have other so-called generation 2 and generation 3. Right. So In conclusion here, that we have been able to develop some so-called analysts, lithium metal battery, and then we have used graphene, sometimes a little bit of graphene combination between graphene and polymer to protect our lithium metal. We can significantly lower the cost of the lithium metal batteries. And because we make use of the very thin lithium anode, or essentially lithium-free in the beginning, then no lithium diffusion issue will occur, and therefore the battery can be charged in less than 15 minutes. And our goal here is to eventually achieve an energy density greater than 450 watt-hour per kilogram, and also greater than 1,000 watt-hour per liter, and then go beyond 1,000 cycle. And of course, along the way, also reduce the lithium-ion battery price down to below $80 per kilowatt-hour. Right now, it's about $110 per kilowatt-hour or so. Okay. So in summary, Global Graphene Group has developed and begun the commercialization of our graphene protective silicon anode material. We had a facility here in Dayton, Ohio, that we are producing approximately 25 metric tons of silicon anode powder material for sale right now. And then it's our plan to expand that out to about 600 metric tons next year. We also have the required technology to overcome the technical barriers of the next generation lithium metal batteries. And again, in terms of graphene-enabled battery, we have worked on not just the lithium metal, but also magnesium ion battery, aluminum ion battery, sodium ion battery, and even lead acid battery as well. We start. Thank you very much, Terrence.
Dr. Yang, thank you. If you want to go ahead and stop share for your screen, we'll go into discussion and take some questions.
Okay.
Thank you. And I'll toss over to Dexter straight away if you have a question right away. Otherwise, I do have a few questions for Dr. Yang.
Oh, go ahead, Terrence. I don't have some questions right away.
Well, one is more just on the business model and approach is, do you see Global Graphene Group, by the way, is one of the most prolific developers of IP for graphene, not just for batteries, but for many, many other applications. And I want to acknowledge that Dr. Yang holds, I believe, if not the highest, close to the highest number of patents. And anybody who follows our newsletter and our patent announcements will recognize his name because you're filing patents quite frequently. So just want to acknowledge the leadership that you've had in driving the technology in this space since early 2000s. My question on the business model side is, do you see yourselves primarily as a producer and supplier of the battery chemistry materials, or have you envisioned or thought about, as some other companies have done, is actually making battery cells?
Okay, that's a good question. I think in the beginning, our business model includes selling the anode material, graphene-enabled silicon, for example, and then graphene-protected lithium metal anode, and also graphene protective sulfur cathode material for lithium sulfur cells and things like that. So we are not in a business of producing cell or battery pack, at least not yet. So our business model really stay in the supply of manufacturing and supplying of the material or component side. Yeah.
And one of the questions from the audience is about the number of cycles. I think you had some statistics. We don't need to bring them up again, but you had some about cycles up to 100 cycles. The question is, what about cycles of the coated silicon anodes after 200 cycles? Do they, at what point basically do you see them degrade? And how does that compare with current typical technology, the graphite lithium-ion cells?
Yeah. We have some silicon anode material that was properly designed. It already exceed 800 cycles. So our goal is beyond 1,000 cycle, actually. So And the 200 cycles in is, I think, for the lithium metal. Actually, our lithium metal also, these are kind of a little bit older data. I cannot show some of the new data for the IP protection purposes. So yeah, our silicon anode material is go beyond, it's already commercialized. It's already go beyond 800 cycles already. So very close to 1,000 cycles.
I have one small detailed question. I assume that you cannot answer it, but I'll ask it anyways from the audience. Is
okay.
The mechanism for actually creating these particles where you have silicon encapsulated, or you also showed some other metallics, gold or other magnesium, I believe, actually encapsulated in graphene. And what is the mechanism or process? How does that even form to coat and then integrate graphene into these small particles, which seem to be I can't remember the exact dimension, but I believe they're sub 1 micron.
Yeah, so the process itself is it's kind of proprietary, Terrence. Yeah, so it's a weight chemistry process. That's as much as I can say. So I cannot go into the details.
Yeah, that's okay. That's what I expected, and we always want to respect IP here. Let me ask you a slightly different question, and that's on as we have noted multiple times, the battery industry itself is a rather conservative industry. They have a lot of invested capital in processes, plants, and procedures to make consistently their products. And so they're very, what should I say, cautious about adopting new chemistries that haven't been thoroughly demonstrated and proven over a long period of time. What is the biggest, or I want to phrase the question this way, what you have shown that you're able to achieve with the improvements is significant with your chemistry. So let's accept that the chemistry itself in graphene works in these materials. What is actually the biggest obstacle to adopting them and seeing them in use in EVs and other battery applications?
Right, and so it has been a long time ago. Actually, we started to work with I cannot name the name out of the NDA. So we have been working with Europe-based EV OEM for quite some time, for more than 4 years now. So they have to thoroughly evaluate your material, and then not just themselves, but also for example, we supply the anode material, and then they will have to hire their cell manufacturer to make it into the battery cell, and then evaluate at the cell level, at the pack level. Eventually, they have to go into the car and then run around there. So that is a very long process. It normally takes 4 to 5 years. Okay, so that is really the obstacle. But fortunately, though, we have been working with them for quite some time. So we are moving toward the end of that type of journey right now. So.
Well, that's it for the time that we have, unfortunately. And Dr. Yang, I really, really appreciate you sharing that. That's quite a lot of information that you shared. We encourage companies that are interested to learn more to contact you directly. And so again, I want to say thank you for your time and sharing a really interesting developments, and congrats on all the progress you guys make. You're constantly pushing that frontier out there. So thank you.